This presentation provides a deconstruction and analysis of the Droid Razr smartphone for ENME473/690. Let's first look at an overview of the phone, including specs and external components. The Droid Razr XT912 was manufactured by Motorola and originally released in November 2011 for a price of $299. The phone weighs 127 grams and features a dual-core 1.2 GHz Cortex-A9 processor, an 8-megapixel camera, and a 1780 mAh lithium-ion battery. When looking at the phone from the front, you'll see the 3.5mm headphone jack, micro USB connector, micro HDMI connector, Super AMOLED display, micro SIM slot, micro SD slot, front-facing camera, power button, volume keys, and buttons. When looking at the phone from the back, you'll see the LED flash, the main camera, the back cover, and the main speaker. The process used to separate the phone into key components and subassemblies will be detailed in the following slides. First, a plastic wedging tool is used to pry apart the two outer covers at the seam. Following the removal of several T5 screws, the battery can be taken out of the phone using a convenient pull tab. After removing several more T5 screws, the inner framework, aluminum chassis, and motherboard can be separated. Finally, the EMI shields are pried off of the motherboard either by hand or with pliers.
The most prominent feature of a smartphone when you hold it in your hand is none other than its display. And these days, as in this phone, the outermost layer of the display is made of Gorilla Glass. So Gorilla Glass is post-processed using a molten potassium bath, which replaces the small sodium ions from the glass with large potassium ions. This creates a residual surface of compressive stress, which improves toughness, preventing small cracks from growing. Another important thing about this display is that it is a Samsung-sourced Super AMOLED display, which is quite different from a standard RGB LCD display. The sub-pixel arrangement here is RGBG and is in a pentile arrangement. Here the blue pixels are significantly larger and lesser in compared to the green and red subpixels, and the reason why they're larger is because they have the least luminous efficiency of the two and they degrade faster, hence the bigger size. After removing the back cover of the phone and removing the battery, we notice an aluminium chassis. Aluminium chassis would provide structural rigidity without contributing to significant weight of the phone, and aluminium has an excellent thermal conductivity and may also play a role in moving heat from the chip-dense motherboard to the phone's periphery. On the deconstruction of this phone, we did not find any dedicated cooling hardware in this phone, such as a copper cooling pipe or thermal interface material placed over the CPU. This might be due to the fact that CPU here consumes very less power at peak. The peak power here rated is 600 milliwatts and the memory, the RAM, consumes 75 milliwatts. We did a very simplified calculation here for the whole package, which emits 675 milliwatts of power. We kept the motherboard at 25 degrees centigrade and the package running at its peak power. The package surface temperature turned out to be 50 degrees centigrade, which is well within the thermal limits of the CPU. During a smartphone use, there are very rare conditions when such a situation might be faced. Hence, the temperatures are well controlled. Another thing to notice here is that there are a lot of EMI shields used in this device. These EMI shields might aid in the transfer of heat within the smartphone, and as mentioned earlier, the aluminium frame might help in transferring the heat from the chip-dense motherboard to the periphery of the phone. A unique thing about this phone is its back cover. The back cover is made of a woven Kevlar fabric, which provides strength while still allowing for significant flexibility. This is much better as compared to glass back or metal back phones, which might crack or dent if dropped. The EMI shields here provide protection from electromagnetic interference to the CPU, the NAND flash, LTE modem, the accelerometer, etc. We did an XRF analysis on the shields and found them to contain 77.5% iron, 16.5% chromium, and 6% nickel. It is important to note that chromium and nickel are added to iron for corrosion and heat resistance. Additionally, these shields might also aid in a better distribution of heat within the smartphone body.
During our analysis of the phone, several techniques were used, which we will show and discuss in the following video. X-ray imaging was used to non-destructively determine the phone's internal layout. We were able to see solder balls, wire bonds, chips, passives, and other components discussed in class. We were also able to determine which components we wanted to analyze further using cross-sections. These selected components were cut from the motherboard using a Dremel, taking care to cut accurately. The cross-sections were then potted in epoxy so that they could be rigidly held in place for grinding, polishing, and observation. The potted cross-sections were then ground using 240, 400, 600, 800, and finally 1200 grit sandpaper. Select cross-sections were polished using a 1 micrometer layer of alumina. The polished cross-sections were examined under an optical microscope, where we were able to see solder balls, interconnect metallization, and various other component internals. X-ray fluorescence was used to determine the elemental composition of different components. A scanning electron microscope was used to get close-up images of a cracked solder ball and the glass fiber fabric.
Now we're going to look at the heart of the phone, the motherboard. Here we have an X-ray and a photo of the motherboard. It's a PCB made of glass reinforced epoxy material such as FR4 with components arranged on only one side. When the Droid Razr was first released, it was marketed as the thinnest phone in the world. So in order to achieve this, designers can only use one side of the PCB in order to reduce the overall phone thickness. This slide highlights many of the major chips and components of the phone. The SanDisk flash at the top, as well as the Motorola LTE processor and Hynix RAM TI-OMAP processor combo chipset at the bottom, were chosen for further cross-sectioning and examination.
We started with the SanDisk flash memory, 16 gigabytes. The picture in the center is the X-ray of the phone without opening or disassembling. On the left, we show where is the location of the memory and how does it look like. And on the right is the X-ray image showing the type of interconnects they have. We have solder balls, as you can see. So we went and we cross-sectioned the parts, as you see in slide 27. On the picture on the bottom left, we have a dark field image, and on the right we have a bright field image. The dark field image, the way it works, it allows us to see more characteristics on the surface structure, like the roughness, sometimes scratches, and allow us to see more, if you see on the bottom of the picture, of the structure of the board. Whereas on the right, the bright field image allow us to see it has more light. The light is directly collected by the lens, whereas in the dark field image, the light does not go directly to the lens. So that's why we have the two different views. If we go to slide 28, we found interesting that at the right of the chip, there was a crack in one of the solder balls. We zoom in, and it was interesting to see that the crack does not go from the top right to the bottom left. On the contrary, it goes from the top left to the bottom right. But if you think this way, the explanation that comes to our minds is that the CTE mismatch, the CTE coefficient for the chip is larger than for the board, which explains why we see this crack going from the left to the right of the ball. We took some measurements of the solder ball, as you can see in the picture on the left, and then we kept taking more pictures, dark field images, because we were able to identify the board, and we can see on slide 29, we can see the fibers of the board in the picture on the left. On the picture on the right, we still have the cracked solder ball, but we can identify clearly the fibers. We were very interested to see how these fibers look like, so we went ahead and took some SEM images, a scanning electron microscope. This works with an electron beam that is shot to a specific location, and the elements absorb the energy from the electrons, and the heavier elements absorb more energy, and we see them as brighter, whereas the lighter elements, they don't absorb that much energy, and we see them like darker. So on slide 30, you can see the picture on the left, the bright area, we can see the solder ball, and interesting, on the bottom of the solder ball, we can see the 7 layers of the PCB. On the picture on the right, we still have the cracked solder ball, and we can clearly see at the top of the solder ball and at the bottom how is the structure of the board. This is, as I mentioned, a 7-layer PCB. And if we go to the next slide, we were very interested to see how the woven fiberglass fabric looked like. If you see in the picture on the left, the bottom left, we can see clearly the 2 different orientations of the fiber. And we went closer, as the picture on the right shows, and we measure the diameter of each fiber, and we found that it was approximately 5 micrometers.
The next chip we examined was the Motorola LTE 2.0 processor. Its location on the motherboard can be seen here, highlighted in blue. This chip provides the 4G LTE connectivity capability for the phone. Initial X-ray imagery of the chip shows this is a fine-pitch BGA package. Within cross-section of the chip, revealing it to be a single-die wire-bonded BGA. To obtain a clearer picture of the wire bond, the sample was cross-sectioned further. The bottom 2 pictures here clearly show the ball wedge interconnection structure of the wire bond. This wire bond was then examined further using a scanning electron microscope. Not only does it show these interconnects in finer detail, but just like the ScanDisk flash chip before, it also illustrates the woven glass fiber structure of these substrates. Next, we wanted to focus on the solder balls for this particular BGA. We did a bright and dark field image with the optical microscope. From these images, the solder balls were measured to be around 260 by 185 microns. We were then interested in the material composition of the solder material. X-ray fluorescent spectroscopy was used on the solder balls, revealing it to be a lead-free sack solder consisting of 79.4% tin, 20.16% copper, and 0.44% silver.
Now, talking about the Hynix RAM and the ENME473 processor, the image here shows the precise location of the part on the motherboard, highlighted in blue. Now, this image shows the X-ray image of the package and clearly shows the ball grid array pattern. Moving forward is the cross section of the same package, and we can see here the RAM, which is connected to the CPU using solder balls, and we can also see the solder balls which connect the CPU to the motherboard. This is a package-on-package assembly, and the CPU itself is a flip chip BGA component. Now in the next image we can see a couple of copper vias here, and we see this particular one via which could be for interconnection or it could be a thermal via. Its exact function could not be ascertained. And moving forward, we also notice a multi-layer ceramic capacitor which is surface mounted onto the motherboard, and it is on the right side of the package as well as to the left side of the package.
As part of this project, the group chose to take a closer look at the vibration motor that is responsible for the vibration of the phone when there is an incoming call or message, or any other type of application that uses vibration. This type of vibration motors are known as ERM, which stands for eccentric rotating mass, usually DC motors due to their high angular velocity. The unbalanced mass creates a centrifugal force. If we will attach this motor to the PCB, this force will be transferred onto the PCB. This centrifugal force will create small displacements. When repeated many times, those displacements will generate vibrations. The centrifugal force in newtons can be computed by multiplying the unbalanced mass in kilograms by its radius in meters by its squared angular velocity in rads per second. Like any other motor, the vibration motor has a product datasheet that will help the user to match the most applicable motor to the required application. In the table, we can see that the typical normalized vibration amplitude is 0.8 Gs. Based on the graph, this typical vibration amplitude is the maximum amplitude that one can get with the most efficient performance of the motor, the efficiency marked with dark olive color. On the right side of the graph also shows the frequency in hertz associated with each of the amplitudes. The frequency information is useful and crucial since the motor is one of the main vibration sources that the PCB and its components experience. The location of the mounted vibration motor was chosen to eliminate failure modes such as mode 1, shown in the picture, by mounting the motor on the board next to well-supported and stiffer location that will prevent big displacement of the PCB. In the picture, we can see that the motor is mounted at the bottom left of the PCB, next to several support locations. Surface mount vibrating motors are secured and connected via PCB pads and reflow soldering. This vibration motor is an SMD, which stands for Surface Mount Device, although it's usually known as Surface Mount Technology, SMT, which is a popular way for mounting electronic components onto a PCB. Due to a smaller footprint, surface mount devices can save valuable PCB real estate in complex applications. Also, SMD components can be automatically assembled to boards with rapid pick-and-place machines. We can see the cross-section of the vibration motor. Like any other motor, we can see some components such as bearings, the shaft, the copper wires that generates the electric field. We can also see that the shaft is slightly wider at the eccentric mass locations, probably due to a press fit process of mounting the eccentric masses.
The majority of the components found in any electronic circuit are passives. Passives are composed by resistors, capacitors, and inductors. And in this particular phone, we have a lot of them. And we selected a region, as shown in slide 53, that has a couple of those. So if we go to slide 54, we cross-section that particular area of the board, and we can see in the top picture 2 surface mount inductors and two two capacitors, ceramic capacitors. We looked them closer, a dark field image on the left and a bright field image on the right, and the copper areas on the surface mount inductor are the coils from this device, and the other area, which is formed by those grains, white, black grains, are actually made of iron, are at the magnetic core of the inductor, which is there to amplify the inductance. Now, if we go to slide 55, we have a conventional multi-layer ceramic capacitor. Um, as you see in the picture on the right, we selected a particular region of that capacitor and we amplify it on the picture on the left. Those lines that you see on the left are the layers of the multi-layer ceramic capacitor. Those layers are made of different conductive metals, but in this one, they're made of nickel, and the rest of the ceramic is made of barium titanate. And it's interesting to see because these components need to be soldered on the board, and ceramic is very brittle. So the primary failure mode and mechanism on ceramic capacitors are cracks in the ceramic. This crack creates conductive paths, and as you see, the separation between the layers is less than a micron. So the type of solder that they select for these devices is crucial on the design and the reliability of these parts. Now, on slide 56, as I mentioned before, we did an XRF analysis to detect the different elements on these passive components. And the first one is on the surface mount inductor. The area on the center that we were most interested is made of iron, 97% of iron, which, as I mentioned before, is there to increase the inductance. It's a magnetic core, which is the center of the coil that forms the inductor. Now, if we go to slide 57, we were interested to see the type of elements that we could find on the ceramic capacitor in this cross section. Roughly 47% is made of nickel, which is the conductive element. 38 is barium, titanium, and copper. Barium and titanium, as I mentioned, was part of the ceramic, which is made of barium titanate. And on the picture on the bottom, we can see the spectrum that was collected by the XRF. We analyzed it and we came with these percentages.